Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we are now going to go on and describe the null space of a linear map. In this topic, we will define the null space of a linear map. We will consider some consequences of this definition. We will look at finding the null space for finite dimensional linear maps. We will see the relationship between the range and the null space, and we will consider the advance and delay operators for discrete time signals. Now, recall that we want to describe the useful characteristics of a linear map. This is not information that we can get at, for example, by looking at the individual numbers within a given matrix. The first two features about a linear map, and specifically matrices, that we are going to describe are the range and the null space of that linear map. The last topic covered the range. Now we will describe the null space. So, given a linear map A that maps a vector space U onto V, the null space of A is the collection of all vectors in the domain that are mapped by A onto the zero vector in the codomain. That is, the null space of A, as represented here, equals all vectors U such that A applied to U is the zero vector. You will note that the null space is a subset of the domain, whereas the range was a subset of the codomain. Again, it is all vectors in the domain that are mapped specifically to the zero vector. Also, the null space of any linear operator is always guaranteed to have at least one element, and that is the zero vector. For the zero vector under a linear map is always mapped to the zero vector in the codomain. Theorem: if A maps a vector space U onto a vector space V, and that map is linear, the null space of A is a subspace of the domain U. Proof: well, if U1 and U2 are in the null space of A, then we must show that a linear combination of these two vectors is also in the null space. But wait a second, A is linear. So if we apply A to the linear combination, then that is simply the same linear combination of A applied to each of the vectors. But both U1 and U2 are in the null space. So both of those equal the zero vector in the codomain, and any linear combination of zero vectors is the zero vector. Thus, a linear combination of vectors in the null space is also in the null space. Thus, the null space is closed under vector addition and scalar multiplication, and so therefore it is indeed a subspace. Theorem: if A mapping a vector space U onto a vector space V is a linear map, and A applied to U is some vector in the codomain, and U sub naught is a vector in the null space of A, then A applied to U plus any scalar multiple of U naught is also equal to V for all alpha in the field. Proof: again, because A is linear, we have that A applied to this linear combination, where one coefficient is 1, is simply that same linear combination with A applied to each of the vectors. Well, we know that A times U, under the assumption, is equal to V, and A applied to a vector in the null space is equal to the zero vector. And of course, any scalar times the zero vector is equal to the zero vector, and any vector plus the zero vector is equal to that vector. Consequently, u plus alpha times any vector in the null space is also going to be mapped to the same value as u. This should sound familiar from previous classes. Here's another theorem. If A, mapping a vector space U onto a vector space V, is a linear map, and both U1 and U2 are mapped to the same vector V, then U1 minus U2 must be in the null space of A. Well, what we have to show is that A applied to this difference of two vectors is equal to the zero vector. And because A is linear, we have A applied to this difference of vectors is that same difference with A applied to each of the vectors. But wait a second, both of those are equal to the vector V, and V minus V is equal to the zero vector. So, a new definition, one that is related to the previous definition we saw of onto, but this is now one-to-one. And you've already heard of one-to-one functions in secondary school. Here, if a map A mapping a vector space U onto V is such that for each U in the domain, the value A applied to U is unique, we will say that A is one-to-one. That is to say, for each vector in the range of A, that vector has a unique pre-image. So if a vector in the codomain is in the range, then there is one and only one vector in the domain that maps onto that vector. A map that is one-to-one is also said to be injective. We will use the terms one-to-one and onto, however. What is one-to-one? Well, you have already seen one-to-one functions in secondary school. A function is one-to-one if different values of t map to different values of y, assuming that y is the vertical axis. You actually tested this using something called the horizontal line test. And that test says that any horizontal line intersects the function at most one point. A linear polynomial a times t plus b with a non-zero slope is one-to-one, as is the exponential function e to the t. Again, the exponential function is not onto the reals, but it is one-to-one. Now, more generally, any differentiable function y of t such that the derivative is greater than 0 for most t and equal to 0 for at most a finite number of isolated points, such a function is one-to-one. And of course, it's also true if the derivative is less than 0 for most t and equal to 0 only for a finite number of points as well. No even polynomial with real coefficients of a real variable is one-to-one. Also, for t greater than 0, ln of t and the square root of t are one-to-one. Finally, a challenge for the better students in the class: prove that every complex polynomial of degree greater than one with complex coefficients is never one-to-one. Theorem: if A mapping a vector space U onto a vector space V is a linear map, then A is one-to-one if and only if the null space is just the zero vector. That is, the null space is a set containing simply one vector, and that being the zero vector of the domain. Proof: if the linear map is one-to-one, then only one vector in U can map onto the zero vector in the codomain. And since we know already that every linear map maps the zero vector in the domain to the zero vector in the codomain, it consequently follows that the null space of A is just the zero vector. Alternatively, assume that the null space is just the zero vector, and suppose that we have two vectors u1 and u2 such that A mapped to each of them results in the same vector. Well, if this is true from a previous theorem, we have that u1 minus u2 is in the null space of A. But wait a second. If u1 minus u2 is in the null space of A, then because the null space has only one vector in it, therefore u1 minus u2 must equal the zero vector in U. Consequently, u1 equals u2. Therefore, A is one-to-one. Now, if a linear map A maps f to the n to f to the m, the null space is found by solving the homogeneous system of linear equations. So, for example, here is a matrix A. Now, it's the same matrix we saw in the last presentation. However, now we're solving the corresponding homogeneous system of linear equations. We're not going to worry about partial pivoting here. So if we just apply row operations and get the matrix in row echelon form, we get the following matrix here. So this matrix tells us that 3 times x5 is equal to 0, so x5 is equal to 0. x4 and x3 are free variables. We have an equation that relates x2 to the free variables x3 and x4, so we can solve for x2, and we have an equation that describes x1 in terms of the other x values. So substituting the value for x2 into that equation and solving for x1, we get that x1 is equal to 6x3 plus x4, the two free variables. Thus, our solution vector is shown here, and we see the solution vector is a linear combination of two vectors. You will notice that these two vectors are linearly independent because the vector corresponding to the free variable x3 is the only vector that has a non-zero entry in the third position, and the vector corresponding to the coefficient x4 is the only vector that has a non-zero entry in or at index 4. So if A mapping f to the n to f to the m is a linear map, then the dimension of the null space plus the dimension of the range equals n, or that is the dimension of the domain. Proof. Well, basically, if A is mapping f to the n to f to the m, it can be represented by an m by n matrix. So convert the matrix to row echelon form with the appropriate row operations. Once it is in row echelon form, each column associated with a leading non-zero coefficient contributes one vector to the basis of the range. Thus, the dimension of the range is the number of columns with leading non-zero entries. Each column associated with a free variable contributes one vector to the basis for the null space. Thus, the dimension of the null space is the number of columns without leading non-zero entries. Well, there are n columns, and each column either has a leading non-zero entry or does not. So, however it works out, the sum of these two must add up to n. Now, if A is a linear map that maps f to the n to f to the m, and n is less than m, then the dimension of the range must be less than m. Proof: the maximum rank of a matrix is the number of columns in the matrix. So the maximum rank is n. Therefore, the maximum dimension of the range is n, as the range can have at most n linearly independent vectors. Thus, the dimension of the range is less than or equal to n, which is assumed to be less than m. But m is the dimension of the codomain, and therefore the range must be a proper subspace of the codomain. Consequence: if n is less than m, the linear map is never onto. Also, if A mapping f to the n to f to the m is a linear map and n is greater than m, then the dimension of the null space must be greater than or equal to n minus m. In other words, the null space must be greater than just the zero vector. Proof: the maximum rank of A is equal to the number of rows, so the maximum dimension of the range of A is m. Now, the dimension of the range of A is therefore less than or equal to m. Also, we can multiply both sides by -1, which means we have to switch the inequality. Combine that with the previous theorem that said that the dimension of the range plus the dimension of the null space is equal to n. Now, add this equation and the previous inequality. Doing this, we see that the dimension of the null space is guaranteed to be greater than or equal to n minus m. And since n is strictly greater than m, therefore the dimension of the null space must be greater than 0. Consequently, if the dimension of the domain is greater than the dimension of the range, the codomain, then the linear map is never one-to-one. Now, if A mapping Fn to Fm is a linear map, then for A to be both one-to-one and onto, it is necessary that n equals m. That is, A is a linear operator mapping f to the n to itself. Proof: for a linear map to be onto, n must be greater than or equal to m. For a linear map to be one-to-one, n must be less than or equal to m. Consequently, for such a matrix to be both one-to-one and onto, the only possibility is that n is equal to m. Important, not all linear operators A mapping f to the n to f to the n are one-to-one and onto. But for a linear map to be both one-to-one and onto, at the very least, it must be a linear operator. Now, if A mapping f to the n to f to the n is a linear operator, that is a linear map that maps a vector space onto itself, then A is either both one-to-one and onto or neither. Proof. If A is onto, then the dimension of the range of A is equal to the rank of A, and therefore that must be equal to n. Thus, as the dimension of the range of A plus the dimension of the null space of A is equal to n, this means that the dimension of the null space must be 0, so therefore the null space is only the set containing the 0 vector, and so therefore A is one-to-one. Let's assume that A is not onto. We will now show that if A is not onto, it is also not one-to-one. If A is not onto, then the dimension of the range of A is less than n. That is, there are vectors in the codomain that are not mapped onto, because after all, the dimension of the range is the number of vectors in any basis. If that basis has fewer than n vectors, then the span of that basis cannot be all of f to the n, because the dimension of f to the n is n. Now, recall, the dimension of the range of A plus the dimension of the null space of A is equal to n. Now, let's add to this expression here. So I took the inequality dimension of the range of A is less than n, and I multiplied both sides by -1. But to do so, in doing so, I must change the direction of the inequality. So therefore, the negation of the dimension of the range of A is greater than -n. So now I can add the inequality onto the equation, and the two dimensions of the ranges cancel each other out, as does n plus -n. Thus we are left with the dimension of the null space being greater than 0. If the dimension of the null space is greater than 0, that means that there is at least two vectors, and in fact infinitely many vectors, that map onto the 0 vector, and therefore A cannot be one-to-one. All right, let's apply these theorems. For this matrix, we note that A must map R6 to R4. At least we're assuming that this is a real matrix. Because 6 is greater than 4, this linear map cannot be one-to-one. It's simply not possible. The minimum dimension of the null space is going to be 6 minus 4, which is 2. So there's guaranteed to be at least 2 free variables. Now, if the rank of this matrix is 4, then this matrix will be representing a linear map that is onto. But if the rank of the matrix is less than 4, then this matrix will not be onto either. Now consider this matrix B. We note that B represents a linear map mapping R3 to R7. After all, it is a 7×3 matrix. Now, because 3 is less than 7, we are guaranteed that this linear map cannot be onto. In fact, the maximum dimension of the range is 3. If the rank of the matrix is less than 3, then the dimension of the range may be even smaller. If the rank of the matrix is 3, then this matrix is 1-to-1, but if the rank of the matrix is less than 3, then there is at least one free variable, and consequently this matrix is not 1-to-1. Now, given this matrix C, we note that it is a linear operator, and so it's mapping R4 onto R4. Because the domain and codomain are equal and they are finite dimensional, either C is both 1-to-1 and onto, or it is neither. Now, if the rank of C is equal to 4, then the matrix is 1-to-1 and onto, but if the rank of the matrix is less than 4, then this matrix is neither 1-to-1 nor onto. Taking a look at the row equivalent matrix in row echelon form, we note that the rank of this matrix C is indeed 4. Thus, this matrix is both 1-to-1 and onto. That means that the range is all of R4 and that the null space is simply the 0 vector. Again, given this matrix, we see it too is a linear operator mapping R4 to R4. Because the domain and codomain are equal, then either D is both 1-to-1 and onto, or it is neither. We can determine this by finding the rank. So if we apply Gaussian elimination with partial pivoting, we find that this matrix is row equivalent to this matrix on the right, which is in row echelon form. We note that this matrix is neither onto, for the rank of the matrix is 3, therefore the dimension of the range is 3, and 3 is less than the dimension of the codomain. Thus, the range is a three-dimensional subspace of R4 that does not equal all of R4. Also, because the rank is equal to 3, that means there is one free variable, and therefore the dimension of the null space is 1. And because the dimension of the null space is greater than 0, that means that it is not 1-to-1 either, for there are infinitely many vectors that are being mapped onto the 0 vector by this matrix D. Now, once again, recall the delay and advance operators on discrete time signals. So if X is this discrete time signal, the delay operator applied to X simply shifts all the entries by 1 to the right, setting the first entry to 0. Well, the only signal that will result in the 0 signal is for the original signal to be the 0 signal. Thus, the dimension of the null space is 0 and is simply the 0 signal. The advance operator, on the other hand, moves all of the entries to the left by 1 and therefore discards x0. Now, for the image of a vector to be the 0 vector, all the entries have to be 0 except for the first one, because the first one is discarded. Consequently, the dimension of the null space is actually 1. So the rule we just saw, that a linear operator is either 1-to-1 and onto or neither, only applies to finite dimensional vector spaces. In this case, both D and E are linear operators on the vector space of discrete time signals. However, D is 1-to-1 but not onto. E is onto but not 1-to-1. Consequently, given a linear map A mapping Rn to Rm by using Gaussian elimination and backward substitution, we can determine the range of that linear map, and we can find a basis for that range. We can also determine if the map is onto. We can determine the null space, and we can find a basis for that null space. We can also determine if the linear map is 1-to-1. All of these are useful properties to understand about a given linear map or operator. Following this topic, you now know the definition of the null space of a linear map. You know that the null space of a linear map is always a subspace, and you know how to find a basis for that subspace. You have become familiar with some additional results concerning the dimension of the null space, as well as a few other properties. You understand the relationship between matrices, the rank of the matrix, and the dimensions of the range and the null space, and you know how to determine a number of properties about the linear map that is represented by a given matrix. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!